Okay, so we're going to talk about properties of rational exponents. And so if you remember back, there's 7 properties of exponents, and all of those properties are exactly the same, whether you're doing whole number exponents or rational exponents. The difference is rational exponents, remember, are my fractions. Okay. So if I have something like 4 to the 1/2 times 4 to the 2/3, all I'm doing is, because the bases are the same and I'm multiplying, I am just going to add those exponents together. So 1/2 plus 2/3. And of course, you could add them off to the side if you want to. We do need common denominators. So we'd have 3/6 plus 4/6, which is 7/6. Okay, so we're going to use these properties as we simplify some expressions. So let me give you a little hint here. As you go through simplifying expressions, remember those properties of exponents and with the multiplication and division. So if you are multiplying or dividing, this does not work when you're adding or subtracting. We'll talk about that in a minute. If you're multiplying or dividing, okay, when the bases are the same, you can combine the exponents. However, when the exponents are the same, okay, you can combine the bases, and that's something we haven't talked about a whole lot, but we're going to look at. So when the exponents are the same, again, not adding or subtracting, but only multiplying or dividing. When the exponents are the same, we combine the bases. So let me show you a couple examples. If I have 8 to the 3rd times, and this is not going to be necessarily those 2 things I just told you, but I'm just going to run through some examples. That's just something for you to keep in mind. All right, so again, I'm multiplying inside here, but my bases are not the same, my exponents are not the same. So what I want to do is I'm going to look at this exponent on the outside, and here I can distribute this inside. You see, this is nothing different than what we've already done. So I get 8 to the -3/2 times 3 to the -2/2. And if you recall what negative exponents do, are they flip. So I've got 8 to the 3/2, and then 2 divided by 2 is 1. So I just get times 3. We're not going to worry about rationalizing this out just yet. We will eventually, but right now I just want you to see how these properties work this way. Let's look at another example here. If I have 5 to the 3/4 divided by 5 to the 1/2, because the bases are the same and I am dividing, remember, it's if I'm multiplying or dividing, then I combine the exponents. So here, the bases are the same, so I'm going to keep that base and subtract these exponents. Now be careful, do not divide these exponents. Remember, the base stays the same. Alright, so 3/4 minus 1/2, and the exponent here leaves me with 5 to the 1/4. Okay? One more. Let's say that I have 4 to the 1/5 times 2 to the 1/5, and I'm going to raise it to the 10th. Now I am multiplying, I'm not adding or subtracting, and I notice that the exponents are the same. So remember what I told you, when the exponents are the same and I'm multiplying or dividing, then I can combine the bases. So this becomes 8 to the 1/5. Now if you combine the bases, don't also combine the exponents, okay? You can only do one or the other, not both. Now because I've got a power to a power, I multiply. So I get 8 to the second power. You can leave it like that, or you can write it as 64, whichever you prefer. Okay, so make sure you know if you combine bases, don't combine exponents. You can't do both, and vice versa. And I'm just going to put vice versa. If you want to put in your notes that if you combine exponents, don't also combine bases, whatever you want, but just know that you do one or the other and not both. So let's see, let's do, all right, I'm gonna let you try 8 to the 1/2 times 9 to the 1/2 raised to the second power. So I'll give you just a second to try it, and then we'll come back together. So looking at this, you notice that the exponents are the same, so that means I'm going to combine the bases. So 8 times 9 is 72. I keep that exponent the same, and now I've got a power to a power, so I get 72 to the first power. Okay? Let's try one more and see if you can get it before we move forward. Let's try 11 to the negative 1/2 times 11 to the 5/2. So I'll give you a second if you'll try this one, and then we'll go over it. The bases are the same, which means I combine the exponents here. So negative 1/2 plus 5/2 would give me 4/2, which is 11 to the second. Again, you can leave it like that, or you can change it to 121 if you want, whatever is best for you. All right, so that's the properties of rational exponents, and they're exactly the same as they were before. We just have some fractions now. Same thing with properties of radicals. Now we know some different types of radicals. We have a third root, a fourth root, and whatever root we want to do. So we want to talk about some properties. So remember, with square roots, we had, if I've got two things multiplied under the radical, I can split them up. And I can go backwards or forwards with this. And the reason that I did this was I was looking for one of these two numbers to be a perfect square so that I could factor it out, right? So for example, if I had the square root of 50, I would want to break that down into 25 and 2, which would give me 5 times the square root of 2, right? So I'm kind of thinking the same properties, and of course we had the division property as well, a over b, square root of a over the square root of b, but then we ran into a problem if we had a radical in the bottom. And so we'll talk about that. But let's look at some properties now that our roots are getting bigger than just a second root, and we can have roots that are 3 and above, any root we want to have. So if I have something like the cubed root of 192 divided by the cubed root of 24. Very important, these roots must be the same, just like the exponents have to be the same. The roots must be the same to combine, okay? And also remember, radicals are exponents. So at the end of the day, the exponent properties still apply. We could change this over to 1/3 and this to 1/3 if we really wanted to. But what I'm going to do is I'm going to put these, I'm going to go backwards on that little property that we talked about just now, and I'm going to do 192 divided by 24 under the same radical. So if you take out your calculator, you'll know that 192 divided by 24 is 8. And what times itself 3 times gives you 8, and you would get 2. Okay, so that's a pretty easy explanation of roots. But what I want to spend a little bit of time on is talking about simplifying roots that are bigger than square roots. Okay, so in other words, if I have a cubed root of something like, or actually let's even go bigger. Let's say I had the 5th root of 64, okay? And I want to take out the biggest root here. Well, what I need to do is make a list. Since I'm talking about 5s, I'm going to make a list of powers of 5 off to the side. So 2 to the 5th is 32. And I can actually stop right there. If I wanted to continue going, I could, and I could have 3 to the 5th equals 243, and already I'm too big to divide into 64. So you'll find that the bigger that root is, the fewer numbers that you actually have to list out. All right, so I'm going to do the 32. So now I get the 5th root of 32 times 2, right? Because 32 times 2 is 64. And so I get 2 times the 5th root of 2. So it's the exact same process that I used before, only now I'm looking at bigger roots, okay? Let me give you one to try. We'll start, let's see. Let's simplify the following first. So by simplify, I want you to combine, and if you can break it up, but simplify this expression. So I hope you've had time to look at this now. So we will simplify first by multiplying what's under those radicals together. So I get the cubed root of 16 times 24 should give you 384. So you get the cubed root of 384. So because I'm talking about third roots now, I'm going to come over here and I'm going to list out some powers of 3. 2 to the third is 8. 3 to the third is 27. 4 to the third is 64. 5 to the third is 125. 6 to the third is 216. Well, if my pen will write. 7 to the third is 343. And so I already know that's as far as I really need to go because I'm looking at 384. So from this list of numbers, I want to pick the biggest one that I can divide 384 by. And I believe it is 64. So I get 64 times 6 would give you 384. So you would get 4 times the cubed root of 6. Okay, so another one for you to try. Let's do the 5th root of 160 divided by the 5th root of 5. So if you'll just take a minute to work this one out. So you should have gotten, if I divide 160 by 5, I get 32. What times itself 5 times gives you 32, and I hope you found that that was 2. Okay, so let's do some simplification with some variables. Okay, so we're gonna work the same way, but we're gonna have some variables thrown in here with our numbers. So let's say I have 8y to the 6th over z to the 12th, and I'm taking the cube root of that. Okay, now here's the thing. Yes, I can split this up. This is the same thing as the cubed root of 8y to the 6th over the cubed root of z to the 12th. But to understand what you have to do with this, you may have to switch this up a little bit to an exponent instead of a radical. So for example, all right, so now I have this. All right, so the cube root of 8, I'm pretty sure everyone is familiar with that, is 2. But the problem is whenever I get to the cube root of y to the 6th and the cube root of z to the 12th, I'm not real sure how to simplify that. So what I really want to do is when I get to this point, I want to change forms on these exponents here. Okay, so remember how to change forms. That's where I make an exponent out of the radical. So here I'm going to have 2y to the 6 over 3. And on the bottom I'm going to have z to the 12 over 3. What's nice about it is these are going to simplify nicely for me. And I have 2y to the 2nd over z to the 4th. Okay? So that's a nice little simplification there for those. Let me give you one more and you try this one. Let's do the 4th root of 81 m to the 4th divided by 16 n to the 8th, and let's see what you get. All right, so let's split it up like we did. Let's do 81 m to the 4th, and let's do 16 n to the 8th, okay? And I'm going to go ahead and take this, I'm going to split this up in the top also. So I have 81 m to the 4th, and I have 16, and I have n to the 8th. So looking at this one, I'm going to skip down here a little bit so I have a little more room. The 4th root of 81, that would be 3. And then I still have the 4th root of m to the 4th power over the 4th root of 16. So let me come over to this side just a minute. The 4th root of 16, I'm going to make a list of 4s here. So 2, oh, I'm just kidding. Come on, 2. Okay, so now what I can do is I can change these to exponents and simplify from there. So I have 3m over 2n, 8 divided by 4 is 2. One more thing to talk about, and that is addition and subtraction of radicals. So before I can combine radicals, I can't combine any radicals that I want to with addition or subtraction. They have to be special. What they have to be is what we call like radicals. And if you think about like terms, it is exactly the same concept, okay? Oh, I said like radicals, and then I started talking about like terms and wrote like terms. Like radicals. So what that means is when I've got this nth root of a, okay, like radicals have the same root, which is n. So the same n and the same a, okay? That's what a like radical is. Now you can have any number you want that sits out front here. Maybe you have 5 times the nth root of a. But the point is that this has to be exactly the same. So for example, if I have the third root of, if I have 5 times the third root of 7, and I have 5 times the 4th root of 7, and I have -3 times the third root of 7. Of all these, this one and this one are like radicals because the root is the same and the number under the radical is the same. Okay, so those are like radicals. So I could actually combine those if I wanted to. I could add those together or subtract them as I needed. When you do that, just like with like terms, if this was 5x and -3x, you only combine the coefficients and you leave the n and the a alone. You leave the root and the number under the radical completely alone. And so sometimes these are set up nicely for us, and sometimes we have to do a little manipulation to get them like that. So let me show you an example. If I have -4 times the square root of k minus 5 times the square root of k, these are like radicals because the root is the same. Remember, there's a little invisible implied 2 here. The number under the radical is the same, so I can combine the numbers outside these coefficients. So I would just say -4 minus 5, which is -9 times the square root of k. All right? The same thing applies if they're rational exponents, because that's just another way to express a radical. So if I had 9a to the 1/3 times b minus 2a to the 1/3 times b, again, these are like terms because this is the same. So I just combine the numbers in front to get 7, and I leave the rest of it alone, okay? So let me give you an example, and you try this one, and let's see what happens. Let's do 6 times the square root of h minus 8 times the square root of h, and see what you get. So I hope you've had time to work this one. When you do this, these are already like radicals. Perfect. I just combine the numbers in front, leave the radical alone, and I'm done. Okay. Let's do one more. Let's make this a little challenging. Let's do 3 times the square root of 5y to the 4th minus y times the square root of 20y squared. And I'm going to give you a hint. Before you start on this one, simplify everything you can first and then see what happens. Okay, so I hope you've had time to do this. So just as I told you, what I want to do, I'm going to simplify these if I can. I'm going to split this up. Because I know that this is a 2 out here. I notice that this is a 4 in here. I know that if I change this form, something's going to happen. So what I want to do, I'm going to change this to 3 square root of 5. I'm going to change to an exponent here, so I get 4 over 2. And if you notice what's happened is the radical has gone away. So I'm going to move it up front with the 3. So I get 3y squared square root of 5. Now all I've done is simplified this portion, okay? I split it up just like I did before. This was an imaginary 2 outside. So then I just made a fraction, 4 divided by 2, to change the form, okay? Let's do the same thing with this one and let's see what happens. I'm going to just look at this radical part. I've got y times the square root of 20 times the square root of y squared, okay? Now I see a couple things in here. The first thing that I see is I know that the square root of any number squared, I know that those cancel out and it just leaves me with y. So I know I have y times the square root of 20 times y. So y and y together would give me y squared, okay? I also know that the square root of 20 I can break down. I can break that down into the square root of 4 and the square root of 5. The square root of 4 is 2, so I still got this y squared out here, times 2 times the square root of 5. So if I write this one kind of like the other one, what I end up with is 2y squared square root of 5. Remember, initially I was subtracting these. I have like terms. Look at this, y squared square root of 5, y squared square root of 5. So all I have to do is combine the coefficients. 3 minus 2 is 1. And I have subtracted those. So of course all of them won't be that hard. That was a little bit of a challenging one, but a great one for that matter. And that is the properties of exponents and radicals.